So I'm Kevin Peterson, although I think most of you know me, the people that remain. For this part of the presentation, I'm going to assume that you already have an IOC, and you already have a motor with support, and you simply want to add stuff to the IOC that you want to use. So maybe you have a motor controller, and you only have 3 axes implemented, or 3 axes when you purchased it, and you bought 5 more, and you now want to use them. It's a very common thing, and it's good to see how it's done. After the slides, I'll actually do some of that stuff. So the pre-built IOC is running a virtual motor, or it's talking to a virtual motor controller that requires Python. It provides 8 axes, but only 3 are currently configured by default. And the aforementioned web page here, does that show up? Yes, it does. Will allow you to download that. So when you want to add motors to an IOC, usually you don't have to look very far. If you're adding motors or an existing controller, and you're just adding a second copy of it, you can probably just look at the IOC's configuration and simply copy and modify those files. If you want to add a new controller, you very likely need to refer to either the motor module or XXX. And even when you're doing that, you still shouldn't have to write anything by yourself. You should just be copying and pasting and modifying a few important values. If you have to do something other than that, we did not do a good job of providing you some examples. So if your IOC is based on XXX, you have a makefile in your IOC source directory that contains all of these lines. And all of this motor support is included by default. And what that means is that if you get a new controller that you've never used before, but it's on this list, if it's made by one of these manufacturers and the driver is on the motor web page, you will very likely be able to add the support to your IOC without having to rebuild anything, which is very convenient and one of the reasons why we recommend people use XXX as a starting point for their IOCs. You'll notice here, to point for the people at home or in the future who see this, the virtual motor driver that I wrote is local to this IOC. It does not come from the motor distribution, and you'll find it in the source directory, and this is how I included it in the example IOC. When you have your new controller or an extra copy of your existing controller, you need to set up how you're going to communicate with it. This presentation focuses on soft IOCs. So I refer you at the bottom of this slide for VME stuff to XXX. But most of the time, your device is either going to communicate over Ethernet or serial. And no matter which one you're using, you're going to call an ASIN call, which I believe is pronounced driv ASIN. So either driv ASIN IP port configure or driv ASIN serial port configure. And you will copy this from an example, and in the case of the IP port, you'll change the Ethernet address and the port number. And for the serial communication, you need to very carefully specify all of the serial port parameters so that they match what your controller needs. We can't tell you ahead of time what a new controller needs, but there should be examples for what the parameters need to be for support that already exists. Again, if there isn't, if you let us know, we can improve our examples. One interesting thing is we are using Ethernet communication increasingly with Moxa servers. So we're using the Ethernet config to talk to serial ports that are connected to the network. And for USB devices, we are using the serial communication setup to talk to devices that present themselves to the OS like a serial device. For the purposes of this example, yes. So this would be like an XPS controller. The virtual motor controller presents itself over the Ethernet just like any other Ethernet-based controller would. So an XPS controller, the hexabaud controller is a variant of the XPS. The Ensemble is just an Ethernet-based controller. So the link, the thing that defines that communication is simply the driv ASIN IP port configure line, where you create a name for the port, the ASIN port that you're going to create, and you tell it where on the network to find it, and then some other arguments that I failed to include the comment in vmc.cmd. One important thing to note is even if you're using the Ethernet communication, your device, if it uses an ASCII protocol, still probably needs the terminators to be set properly. If you don't set the communication terminators to match what your controller needs, you will very likely have lots of problems talking to it. Sometimes that means you won't communicate at all. Other times that means you may get every other call response, and your status might be interpreted as a position, and you get all sorts of problems. So it's very important that this configuration matches whatever the controller actually needs. The virtual motor controller is a Model 3 driver, and it is incredibly simple. It was written to basically accept everything that the motor record sends to it. And when you're configuring it, you get standard ASIN Model 3 options. You create a new named port that is going to be used for that motor controller. You specify the previously created ASIN port that is used to communicate either over the network or over serial with it. You tell it how many axes you want, and then you set some polling periods. The polling periods are in milliseconds, which is helpful to know. And you can see here there are a few examples of differing idle polling periods. You might want to change the idle polling. If you are doing some troubleshooting, you might not want any idle polling, because your idle polling will stream messages and interfere with what you're trying to debug. By default, I use a 10-second idle polling so that you can see communication, but it's not overwhelming. And the last line is an example of more motors. If you'd like to see an example of a very complex controller setup, I refer you to the Newport XPS controller. It is different in that it needs information that you can't automatically determine to be specified when you create the axes for the controller. So in addition to calling a motor create controller line, you have to call axis create lines and tell it how many steps per unit. You have to tell it the name of an axis, otherwise the support just doesn't work. After you've configured the driver and the communication and the driver, you have to configure the records. And usually the records are loaded in a substitutions file with a db load template line. You'll notice that for the VMC IOC, this is commented out because by default I wanted it to be easy to use, and so the default 3 motors don't require any manual configuration. If you wanted to add motors, you would need to uncomment this line and modify the substitutions file to change the prefix, because the prefix is hard-coded in this line, and it's hard-coded in this file, and it can't be specified by an environment variable. It's important to note that the values specified in this substitutions file will be overwritten at IOC and NIT if you are autosaving motor parameters, if you're autosaving the motor fields. That doesn't mean you shouldn't set these. These are excellent defaults in case autosave fails, but these values will only effectively take effect the first time before autosave takes over. One important thing to note is that if your controller has a non-zero position when IOC and NIT happens, the autosave value will not be restored. The assumption is that if your controller has a non-zero value, it must know where it is, and so the autosave value is discarded, and your controller is just trusted to be the authority on what the position should be. This is actually an issue because when you soft reboot a VME, your positions in your OMS controllers don't get reset. So you can sometimes find yourself in a situation where you thought something was being restored and it was not. After you've added your motors to your IOC, you generally add your new motor channels to MEDM, and these are the standard edit screens. All of this has been done for the example IOC, so there should be no need to modify anything in MEDM to run the example IOC. The example IOC also contains the soft channel device support example that has been on the motor record documentation for many, many years that many people have not tried to run, but it's a fun thing to run to see how that works. It's a tangent arm example where you have a tangent arm that has a linear EGU and the degrees. That's the soft motor. So I will show that after we're done. These are all the slides because I wanted to get to the more exciting demo part. If anyone has any questions, I can answer them now, or I can just skip to the fun, tricky stuff that you might not have realized that the motor record provides. Cool. So, to actually do what I've just showed, I need to run my soft IOC. And because I wrote the instructions, I know I need to change its prefix in case someone else is running the same IOC on the same network. And I have a start VMC1 Windows batch script, which runs the Python script, which looks like nothing. We can start MEDM eventually. And we can pull up motor screens and see that they're white, our favorite MEDM screen state. And so the IOC, as it is configured, will run and doesn't, other than changing the prefix in that environment file at the top, does not need any additional modification by hand to make it work. You'll notice that at IOC init, there were a lot of complaints because none of the autosave files existed. After the IOC boots, it will say, I'm creating the files, and from that point forward, you can sleep soundly knowing that your values are being autosaved. So there are 3 axes. When you tell motors to move, you can see that the Python script is telling you that something's actually happening. You can also see them moving. It's a little unfortunate that I took away the most satisfying part of moving a motor, which is seeing the axis spin by writing a virtual controller that provides you absolutely no feedback. But it's convenient for running when you don't have any other requirements, hardware requirements, electrical requirements. So you now have a virtual controller that is in a state that you will likely find yourself at some points, which is, I have an 8-axis controller, I bought 5 more axes, and now I want to use them. So we need to add those axes. And the substitutions file that was mentioned in the slides lives in your IOC boot IOC VMC directory, which we will quickly edit to get to the good stuff. We'll do this. That doesn't do what I think. I'll do this the hard way, but I could very well just do a global replace. But then you wouldn't hear all the key presses. This was already configured reasonably well. It's not a perfect configuration. the ends are already incremented properly. If you copy from another example substitutions file, you need to ensure that your ends, if your motor name is going to use an N macro, that these are not duplicated. There are no duplicates. You need to make sure that the port matches the port that you specified when you called the create controller line in your CMD file. And you need to make sure that the addresses are unique also. So the difference is that at the top of the substitutions file, when you have a block here that you're loading, the database here defines the fields that you need to specify. It defines the pattern that needs to be fulfilled to load the records without error. So if you look in this ASIN motor database file, which is probably a good thing to do at this point, Kevin desktop, Kevin vmcdb, ASIN motor.db, you see a motor record that is loaded, and all of these macros need to be specified, otherwise you have an empty field, and you can't have an empty field when you load that record. Now, you'll notice that retry is different than the rest. We recently added a default for retry. So if you leave retry out of your substitutions file, you get 10 retries by default, which is a convenient way to reduce the number of columns that you need in the substitutions file. We could very easily put in a default for all of these, or most of these, and then you might only need 5 or 6 columns. And you could always add a column if you wanted to specify that value to override the default, but that's not currently how it's done. A different database, motor.db, would be loaded for motors with older driver architectures. So now that these motor records are added to the substitutions file, or I should say now that the substitutions file is reconfigured, and we want to increase the number of motors in the IOC. So here, we probably don't want 3 because we just paid good money for 5 more. So now we have 8. We also want the settings to be auto-saved and the positions to be auto-saved. Although doing this incorrectly the first time is a good way to remember how important it is to do it. But let's not do that today. And then we can relaunch the IOC and have the satisfaction of seeing new MEDM channels populated. So the IOC dies, and then the IOC comes back to life. And then if I haven't made a mistake, I made a mistake. And I can show you what the mistake is. So the mistake that I made was that I ran the wrong script. Usually we start IOCs using scripts in the IOC boot directory, but this example does not. This example uses the scripts at the top to try to do it in a more dynamic way that requires you to configure less. You see error messages here after the boot because it couldn't find values to restore for the new motor channels that it now knows it's auto-saving. You only see that the first time. So if we wait 30 seconds and restart the IOC, you won't see these messages anymore. Actually, you probably will. No, you won't. No, you won't. So MEDM is, yes. And I made another mistake, which is a good thing to see. I modified a substitutions file, but I failed to include it in the IOC's boot because the way that I've done this, that is not all that needs to be done. the 3 motor records were loaded using DB load records instead of, try that again. Now we have new motors. Very, very exciting. Now we have 8 motors, and in theory they all move. So one of the things that I've done is that I've misconfigured the MRES for the additional 5 motors based on the way the virtual motor controller is written, so that if you go to the motor all screen for one of the new motors and one of the motor all screens for the original 3 motors, you'll see that the MRES is 4 times too large. If we did actually have a spinning axis right now, when we tweak this new motor 1 unit, you would see it move a quarter of a rotation instead of a full rotation. It was intended to be an exercise that could be done, but that's not particularly interesting. So let's move on to more interesting things. Okay. You could add an additional controller in a similar way by copying this motor controller's configuration. If you make a copy of vmc.cmd, you can add another controller with 8 axes. We're going to skip that. We're going to get on to the tricky motor stuff because it is more important, I believe, at this point. So, we have an IOC running. We have some motors. You've used motors before, but you may not have realized that there are quite a few things that can get in your way and cause problems. The motor record has a lot of fields on the screen that Ron showed you in the previous talk, and one of them is MIP. MIP tells you something about the internal state of the motor controller. One of the most common reasons you will find yourself looking at MIP is because you will want to know what caused your motor to move. If there is an external move, there is a bit in MIP that you see. It's 8,000 in hex, but that's not important right now. The important thing is, with ASIN motors, you can move a motor, or even without ASIN motors, with a motor that you can move from the front panel, you can run into a situation where your motor's position is inconsistent with what is in EPICS, with the target position in EPIC. If we move this motor, the way that I move a virtual controller from its front panel is by telnetting into it. So you can see that the motor here is currently at 1, which corresponds to a raw position of 400. The virtual motor controller operates in raw units. So if I move the motor to 2000, I must have disabled idle polling without realizing it, or didn't wait 10 seconds for the idle poll to happen. Now you can see that a status update happens and the motor readback is out of sync with the target position. Now, the maintainers of the motor record have recognized that this is a problem, and they've given you a field called sync, which lives right here above the direction field, which you probably have never used. Sync, in this scenario, will set the target position to be equal to the readback, because if I tweak right now, we will move the motor from relative to the target position, which is 1, as opposed to the readback position, which is 5. If that value is wildly different, you can easily collide a motor without realizing it when you just tweak, because tweaking is an easy way to move a motor if you don't notice that there is a discrepancy. So you click sync, magically everything's in sync, and you're good. So sync is a very useful feature, especially if you're doing soft motor things that doesn't get a lot of attention. Ron mentioned disabling limits. this is something that the beamlines do reasonably. They do it infrequently, but it does get done. So if we set the limits to, say, 6, and we tried to move 2, it says soft limit violation. If I don't want that to be a limit, you can disable them, and then you can move anywhere you want. Now, there is currently a problem with this, which is that if you have an offset, your user limits now look like they're both set to 5. However, so on this screen, the one that your user is likely to see, which is not that one, which is this one. No. Medium setup? Okay. Either way, the user coordinates give you the impression that you should not be able to move the motor right now, and yet you can. Because the motor is not actually disabled, because the dial coordinates don't. You disable the motor's limits if you set the dial coordinates to 0. So you can't tell if a motor is disabled by simply looking at the user units. It is not uncommon for beamlines -100 to disable a motor by setting the high and low limit to the same value to try to stop a user from moving a motor in either direction. And one of the reasons I believe they do this is because spec doesn't like it if you disable the record, because it's always writing the target position to the motor when spec moves things. So there are some gotchas there. Let's set these back to reasonable levels and continue on with a few other things that might make your day miserable. So there was some talk about VBase in the earlier talk, and VBase is useful, but sometimes VBase is set high, and I believe there was a question that what if you set VBase equal to your Velo? Now, for many controllers, this might not be an issue, but if you have a smart controller, the driver will send an acceleration of 0 to the controller in this configuration, because that's what acceleration is required. And some controllers will not move if their acceleration is set to 0. You might find in this configuration that your motor does not move at all. That has happened on at least one of my beamlines. Let's see. The jog feature doesn't get used all that often, but it's very convenient. It's important to understand that when you're using the MED-M screen and you're holding down the button and it's moving, and you let go, the jog stops. But the reason the jog stops is because the motor record is stopping the motor. If you were to lose your connection to the IOC while you were holding down the jog would not stop, because it would not see that your motor the button was released and that put was sent. So in general, while jog is very convenient, you generally don't want to use CA puts to initiate the jog, because you need another CA put to stop the jog. And you can get into situations where the motors run away. The motor record, this is a slightly more advanced gotcha. The motor record is designed in such a way where it is assumed that you will only change one field at a time. If you change multiple fields at a time, it's not always obvious what will happen, and what will happen is not usually what you want to happen. And that might seem, how do you even change 2 values at a time? If you use any calcs or calcouts or transforms, by default, all of your out fields have an NPP output link. That's the default property of the outlink. Change a value in the motor record, but not cause it to process. So in the past, there have been situations where if you put the motor in set mode and you give it a new position, and then you click stop, and then you let go, or you get out of set, the motor would move. But we fixed that bug, so that didn't happen right now. But it is possible in a standard IOC with standard user support, like very useful calc outs, enabled calc outs, to do that. Because, just to show, KMP, M1, NPP, NMS. So by default, I can cause trouble with my motor record. It's a toss-up. It's a toss-up whether or not that's a problem or not. It depends on which fields you modify. There's one field in particular that I think you might want to change on a regular basis if you are a slightly more advanced user, the sort of user who might use some calc records to do a calculation to update motor fields frequently, and that is the acceleration field. Your acceleration time is usually fixed. You're fixing the acceleration time, but when you change the speed, I'm going to double my speed, I have now also doubled my acceleration. Because I need to get up to a speed that's twice as large in the same amount of time. So for a lot of controllers, that's probably fine. But for some controllers, like the XPS controller, each axis has a maximum acceleration that's defined. And so depending on how you set your acceleration time and your speed, you can get yourself into a situation where the XPS controller will return a very vague error message, -22, not allowed action. It doesn't tell you what's wrong. It just says you're not allowed to do that. And you can spend a lot of time trying to figure out what's wrong before you realize that, hey, that speed combined with that acceleration time results in an acceleration that's slightly above my internal max acceleration. We should mention, because I have a few minutes before noon, which I think is an excellent stopping point, you can get yourself into a lot of motor configurations with limits that are very confusing. So let me just move some of these away. Because your direction can be negative, and your MRES can be negative. And I think the reason the negative MRES didn't work in the other, actually I don't really know what that means. When you start changing offset and direction and motor resolution, it can not be obvious how the limits are and the positions are going to respond. Related to that, you can also get into somewhat confusing situations with the direction and the MRES and the backlash distance. With the MRES and the backlash distance both being signed, I don't know that I could tell you off the top of my head what would happen if I made a backlash move with everything negative. That must be the preferred direction. Negative, negative, negative means positive is the preferred direction. So being aware that the backlash distance is signed, that the MRES is signed, that the DIR field exists. So for the virtual motor controller, you can see here from its MSTA detail field that it does not support closed loop control. Because it does not support closed loop control, this torque enable disable is going to do nothing. If gain support was set to yes, toggling enable torque to enable or disable would change the state of the position bit, which would tell you if closed loop control is enabled or disabled. On a servo motor that, like an air bearing stage, disabling torque would literally disable torque, most likely, and then you could spin the stage freely. And so you'd probably always want that to be enabled. This torque enable field is the CNEN field, and it is both a readback and a control. a good driver should set that properly so that you can see if the torque is actually enabled or not. So this is a controller enable disable that is meaningful for certain types of motors. Where is that option? Don't show me this message again. Thank you for pointing that out. That was really annoying. This enable disable closer to the top of the motor X all screen is a record motor enable disable. So if I had that CMD window open to the directory where the CA put was, and if I'm lucky, I have not pasted anything since then. The record disable prevents, I can't remember if it prevents CA puts and database writes or both. It prevents you from writing to the motor record. So in theory, let's see if this pastes. Awesome. CA put KMP M1. So I get an exception. I'm not allowed to do a CA put to that motor when it's in the disabled state. If you don't use spec, this is a reasonable way to disable motors so that users don't accidentally move them, because Epics won't let you move it from a CA put. There are other ways. In a calc record, it does not use CA put unless you explicitly tell it to. You can still move things. It's difficult to really disable a motor record. There isn't a nice indication. There is not a nice indicator on this screen to show you that it's disabled, but I believe the other ones do. If I go to exceed, yes, the black and red around the motor. And the functionality that provides that enable disable for the record is present in all of the records. You can, if you would like to, disable just about any record, because that's one of the features that I believe is common to most record types, maybe all. It's been a long time since I've looked that up in the record reference manual. So the encoder resolution you would use if you set use encoder to yes. And there are some controllers, like an XPS controller can drive an axis that has an encoder. And the driver puts the encoder position here and the target position, the theoretical position there in the motor position thing. If you use the motor position, so if use encoder is no, you get a very stepper motor-like behavior. You probably never have any error. The motor always looks like it gets to exactly where it's going. There won't really be any retries unless something strange happens. If you set use encoder to yes, it will use this encoder readback instead of the motor position for the raw readback. It also tells the motor record that it should do relative retries. So if it makes the move and it finds that it doesn't get to its target position, the motor record will look at the error and do a retry of the relative distance that corresponds to the error to try to close that gap. And in theory, after a few retries, you get to your position. Depending on how sloppy the relationship between your target position and the encoder is, this could be a very good thing or a very frustrating thing. Use readback, as Ron mentioned, can be used for talking to an external encoder or any other PV that I want to provide the readback. And the danger that you run there is if you're using the readback as you are, I didn't show you the soft motor. The soft motor example uses this readback in link. If your calculation is slow for some reason, like if your calculation isn't residing in the IOC, if you have another piece of software that's doing a complex calculation and putting the value to the PV that's used to link in, you might find strange motor behavior. because the motor record expects the readback to behave in very specific ways. If the first time it does a status update, it doesn't see that readback changing, you start to run into problems. You'll see error messages on your IOC. The motor record will give up at some point if your calculation's too slow. Calculations aren't usually that slow, but it's something to take into account.